What if everything you touch, see, and breathe isn't made of tiny solid particles, but of something far stranger, invisible strings vibrating in dimensions you can't even imagine? Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind drift off to sleep. Tonight, we're venturing into one of physics' most beautiful and bewildering ideas: string theory. It's a theory that suggests reality itself might be woven from something as delicate as music, where every electron and every star is really just a tiny string vibrating at its own special frequency. It's physics that sounds like poetry, mathematics that feels like magic. Before we begin tonight's gentle journey through dimensions both hidden and vast, feel free to share what time it is and where you're listening from. There's no need to follow every detail, just let the gentle current of curiosity carry you wherever it will. So settle in, close your eyes if you like, and let's take a slow, peaceful journey into the extraordinary possibility that everything, absolutely everything, might be made of music. Physics has a problem, and it's been keeping scientists awake at night for nearly a century. Imagine you're trying to understand a beautiful, complex song. You have two different ways of listening to it. One method works perfectly for the high notes, the delicate melodies, the quick trills and whispers. The other method captures the deep bass, the powerful rhythms, the way the music moves through the room. Both methods work wonderfully on their own, but when you try to use them together to understand the complete song, they give you completely different, contradictory answers. That's essentially the predicament modern physics finds itself in. We have two incredibly successful theories about how the universe works, and they're like oil and water, they simply refuse to mix. The first theory is called quantum mechanics. It describes the behavior of the smallest things in the universe with stunning accuracy. Atoms, electrons, photons, all the tiny building blocks of reality dance to quantum rules. These rules are strange and wonderful. Particles can be in multiple places at once, can tunnel through barriers that should be impossible to cross, can be connected across vast distances in ways that seem almost magical. Quantum mechanics has given us computers, lasers, MRI machines, and smartphones. It works so well that some of its predictions have been confirmed to more than 10 decimal places. The second theory is Einstein's general relativity, and it governs the large-scale structure of the universe. Gravity, space, time, black holes, the expansion of the cosmos, all of these fall under relativity's elegant mathematical umbrella. It tells us that massive objects warp the fabric of space-time itself, that gravity isn't a force pulling on objects, but the result of objects following curved paths through bent space. General relativity predicted the existence of black holes decades before we found them, explained the orbit of Mercury, and told us the universe was expanding long before telescopes confirmed it. Both theories are triumphs of human understanding. But here's the problem. When physicists try to apply both theories to the same situation, the mathematics breaks down completely. It's not just that they disagree, it's that they produce infinite, meaningless answers. Imagine asking two friends what time it is, and one says 3 o'clock while the other starts reciting the entire works of Shakespeare backward. That's roughly the level of confusion we're dealing with. This becomes particularly troublesome when we try to understand situations where both quantum mechanics and general relativity should apply. The interior of black holes, for instance, or the very first moments after the Big Bang. These are places where the universe is both incredibly small, so quantum affects matter, and incredibly massive, so gravity dominates. Our current theories simply can't handle these extreme conditions together. And so, physicists have been searching for what they call a theory of everything, a single framework that could describe all the forces of nature, from the quantum to the cosmic. It would be like finding a universal language that could describe both the whisper of an electron and the roar of a black hole, both the delicate quantum dance inside atoms and the grand waltz of galaxies through space. String theory is one of the most promising candidates for this theory of everything. It's an idea so radical, so mathematically complex, and so far removed from everyday experience that it sounds more like science fiction than science. But it might just be the key to understanding why the universe works the way it does. The basic idea is both simple and profound. What if all the particles we think of as fundamental, electrons, quarks, photons, aren't actually fundamental at all? What if they're all made of something even more basic, tiny vibrating strings of energy? These strings would be unimaginably small, far smaller than atoms, far smaller than anything we could ever hope to see directly. They would vibrate in different patterns, like the strings of a violin or guitar, and each pattern of vibration would correspond to a different particle. It's a beautiful thought. The entire universe, from the smallest quantum particle to the largest galaxy, could be nothing more than a vast symphony of vibrating strings, each playing its own note in the cosmic composition. And if that's true, then the theory of everything isn't just a mathematical framework, it's literally music made manifest. But before we get too carried away by the poetry of it all, we should remember that string theory is still very much a work in progress. It's incredibly mathematically complex. It makes predictions that are almost impossible to test with current technology, and there are aspects of it that even its strongest supporters find puzzling. Still, the fact that such a theory exists at all, that mathematicians and physicists have managed to construct a framework that might, just might, explain everything from quantum mechanics to gravity in terms of vibrating strings, is quietly extraordinary. It suggests that reality might be far more elegant and interconnected than our everyday experience suggests. Imagine if the smallest things in the universe weren't actually things at all, but songs. For most of the 20th century, physicists thought they understood the basic building blocks of reality pretty well. Matter was made of atoms, which were made of protons and neutrons and electrons. Then we discovered that protons and neutrons were themselves made of even smaller particles called quarks. We found particles that carried forces, photons for light and electromagnetic fields, gluons for the strong nuclear force, W and Z bosons for the weak nuclear force. It was like taking apart a watch and finding springs and gears and tiny wheels, each with its own specific job. We built what's called the Standard Model, a kind of periodic table for all the fundamental particles and forces. It worked beautifully, explaining almost everything we observed in particle accelerators and cosmic ray detectors. But there was always something slightly unsatisfying about this picture. Why these particular particles? Why these specific masses and charges? Why do electrons have exactly the charge they do, and not some other value? The Standard Model could describe these properties with incredible precision, but it couldn't explain why they existed in the first place. And then, sometime in the late 1960s, a few physicists began playing with a radical idea. What if these fundamental particles weren't actually fundamental? What if they were all different manifestations of something even more basic? The idea they came up with sounds almost musical. Instead of thinking of electrons and quarks as tiny solid points, what if they were actually tiny loops of vibrating energy? These loops would be unimaginably small, perhaps 10 to the minus 35 meters across. That's so small that if an atom were scaled up to the size of our solar system, a string would still be smaller than a tree. But size isn't what makes strings special. What makes them remarkable is that they can vibrate in different ways, like the strings on a guitar or violin. And here's the truly elegant part. Each different vibration pattern corresponds to a different particle. Picture a guitar string for a moment. Pluck it one way, and you get a low, deep note. Pluck it differently and you get a high, bright tone. The string is the same string, but the different vibration patterns create completely different sounds. In string theory, something similar happens. The same fundamental string, vibrating in different patterns, appears to us as completely different particles. A string vibrating in one particular way might manifest as an electron with its specific mass and electric charge. The same string vibrating in a different pattern might appear as a photon, massless and carrying light. Another vibration could produce a quark with its own unique properties. It's as if the entire particle zoo, all the electrons and photons and quarks and neutrinos, were really just different notes being played by the same cosmic instrument. This idea is breathtaking in its simplicity and scope. Instead of dozens of fundamental particles, each requiring its own explanation, we would have just one fundamental entity, the string. All the complexity and diversity of the particle world would emerge from the simple fact that strings can vibrate in many different ways. But strings in string theory aren't quite like guitar strings. For one thing, they don't need to be attached to anything. They can exist as tiny loops, closed circles of vibrating energy floating freely in space. They can also exist as open strings with two loose ends that can wiggle and dance. And unlike guitar strings, which vibrate in the familiar 3 dimensions of everyday space, these fundamental strings vibrate in additional dimensions that we can't directly perceive. The mathematics of how these strings vibrate is extraordinarily complex, involving concepts from some of the most advanced areas of mathematics and physics. But the underlying idea remains elegantly simple. Everything is music. Every particle, every force, every field is really just a different song being sung by vibrating strings. There's something deeply satisfying about this picture. Music has always seemed to touch something fundamental about reality. We talk about the music of the spheres, the rhythm of the seasons, the harmony of natural processes. String theory suggests that this might be more than just poetic metaphor. It might be literally true that the universe is a symphony, with every atom and every star contributing its own voice to the cosmic composition. Of course, we can't actually hear this music. The strings are far too small and their vibrations far too rapid for our ears to detect. But in some sense, we are the music. Every atom in your body, every thought in your mind, every beat of your heart would be part of this vast, invisible symphony. The idea that particles are really vibrating strings also helps explain why the mathematical constants of nature have the values they do. Just as a guitar string's pitch depends on its length, tension, and thickness, the properties of fundamental particles would depend on the precise way their corresponding strings vibrate. The mass of an electron, the strength of the electromagnetic force, the speed of light itself, all of these might be determined by the underlying geometry and dynamics of string vibrations. It's a picture of reality that's both more complex and more unified than anything we've imagined before. Complex because it requires additional dimensions and mathematical structures far beyond our everyday experience. Unified because it reduces all the apparent diversity of the physical world to variations on a single theme, the music of vibrating strings. Whether this musical vision of reality is correct remains one of the great open questions in physics. But the very fact that such a theory is mathematically possible, that the laws of mathematics allow for a universe where everything is made of music, is itself a kind of wonder. Right now, as you listen to this, you might be surrounded by dimensions you can't see, touch, or even imagine. We live in a world of 3 spatial dimensions. You can move forward and backward, left and right, up and down. That's it. Those are your options for getting around in space. Add in time as a 4th dimension, and you have what physicists call spacetime, the arena in which all of physics takes place. But string theory suggests that this familiar picture is incomplete. According to the mathematics of vibrating strings, reality might actually have many more dimensions than the 4 we experience. Not just 1 or 2 extra dimensions, but perhaps 6 additional dimensions of space, making a total of 9 spatial dimensions plus time. Now, this immediately raises an obvious question. If there are extra dimensions all around us, why can't we see them or move through them? It's not as if we can step sideways into a 5th dimension the way we can step sideways across a room. The answer, according to string theory, is that these extra dimensions are compactified. They're rolled up, folded, and curled so tightly that they're effectively invisible to us. Imagine looking at a garden hose from a great distance. From far away, the hose looks like a simple one-dimensional line. You can see its length stretching from one end to the other, but you can't see that it actually has width and depth as well. The hose is really 3-dimensional, but 2 of those dimensions are curled up into such a small circle that they're invisible from a distance. In string theory, something similar might be happening with space itself. What we perceive as a point in our 3-dimensional space might actually be a tiny, complex shape in 9 dimensions. The extra dimensions are there, but they're curled up so small, far smaller than atoms, that we have no way of directly experiencing them. Think of it this way. If you're an ant walking along that garden hose, you can move in 2 very different ways. You can walk along the length of the hose, traveling large distances that anyone watching from far away can easily see. Or you can walk around the circumference of the hose, following a tiny circle that brings you right back to where you started. From the ant's perspective, both directions are equally real. From our distant perspective, only the motion along the length of the hose is visible. We might be like observers watching from far away, able to see motion in the 3 large dimensions of space, but completely unaware of the tiny circular journeys that might be possible in the compactified dimensions. But these hidden dimensions aren't just mathematical curiosities. In string theory, they play a crucial role in determining the properties of the particles we observe. The way the extra dimensions are curled up, their shape and size, affects how strings can vibrate within them. And since different vibrations correspond to different particles, the geometry of the extra dimensions would directly influence the physics we observe in our 3-dimensional world. It's a bit like the way the shape of a musical instrument affects the sounds it can make. A violin and a guitar might have strings of similar length and tension, but they produce very different sounds because of the different shapes of their bodies. The wood, the curves, the internal cavities all contribute to the final music. In string theory, the hidden dimensions play a similar role. They're like the body of a cosmic instrument, shaping and coloring the vibrations of the strings in ways that determine which particles exist and what properties they have. This leads to one of the most remarkable predictions of string theory. There might be many different ways to curl up the extra dimensions, and each different configuration would correspond to a different possible universe with different laws of physics. Our universe, with its particular particles and forces and constants, would be just one of many possibilities, the result of one particular way of folding up the hidden dimensions. The mathematical shapes that describe these folded dimensions are often fantastically complex. They have names like Calabi-Yao manifolds, after the mathematicians who first studied them. These shapes exist in 6 dimensions, which is already hard enough to visualize, but they have intricate internal structure with holes and tunnels and connections that would make a 3-dimensional maze look simple by comparison. And yet, despite their complexity, these hidden shapes might be everywhere. Every point in space, every location where you could place your finger might be not just a point, but a tiny, incredibly detailed 6-dimensional sculpture. The space around you wouldn't be empty but filled with structure so fine and folded that it escapes all notice. There's something both humbling and wonderful about this idea. It suggests that reality is far richer and more complex than our senses can detect. We move through the world thinking we understand space, thinking that what we see is what there is. But we might be like creatures living on the surface of a vast ocean, completely unaware of the depths below. The hidden dimensions also offer a possible solution to some long-standing puzzles in physics. Why is gravity so much weaker than the other forces? In string theory, gravity might be diluted by spreading out into the extra dimensions, while the other forces are confined to our three-dimensional brain, our slice of the higher dimensional space. Of course, the existence of extra dimensions remains purely theoretical. We have no direct evidence for them, no way of seeing or measuring them with current technology. They exist in the mathematics of string theory, but whether they exist in reality is still an open question. But the possibility alone is enough to change how we think about space and existence. It reminds us that the universe might be stranger and more wonderful than our everyday experience suggests. Right now, as you rest and let your mind wander, you might be floating not just through the familiar dimensions of space and time, but through hidden dimensions folded so tightly they fit in the space between your thoughts. What if gravity, electricity, and the forces that hold atoms together were all just different instruments in the same cosmic orchestra? In our everyday world, we experience forces as very different things. Gravity keeps your feet on the ground and makes apples fall from trees. It's always attractive, always pulling things together, and it seems to work across infinite distances, though it gets weaker as things move apart. Electromagnetic forces give us lightning and magnetism, run our electrical devices, and hold atoms and molecules together through chemical bonds. Unlike gravity, electromagnetic forces can both attract and repel, and they're much stronger than gravity, but they can also be shielded and blocked. Then there are two forces we don't experience directly, but that are crucial for the existence of matter itself. The strong nuclear force holds the centers of atoms together, binding protons and neutrons despite their tendency to push apart. The weak nuclear force is responsible for certain types of radioactive decay and plays a key role in the nuclear reactions that power the sun. For much of the 20th century, physicists treated these four fundamental forces as completely separate phenomena, each requiring its own mathematical description, its own set of rules. It was like having four different orchestras playing in different concert halls, each with its own conductor, its own sheet music, its own style. But gradually, physicists began to notice connections. In the 1960s and 70s, they discovered that the electromagnetic force and the weak nuclear force were actually two aspects of a single unified electroweak force. At high energies, or equivalently at very high temperatures like those just after the Big Bang, these two forces become indistinguishable. They merge into one. This was like realizing that two different orchestras were actually sections of the same larger ensemble, playing in harmony according to the same underlying score. The discovery earned several physicists Nobel Prizes and suggested that the apparent diversity of natural forces might be an illusion, that at a deeper level there might be more unity than anyone had imagined. Scientists then began trying to unify the electroweak force with the strong nuclear force, creating what they called grand unified theories. These theories suggested that at even higher energies, all three of these forces would merge into one. Some of the mathematics worked out beautifully, but the theories also made predictions that didn't match what we observe in nature, so the picture remained incomplete. That left gravity as the odd one out. Gravity has always been different from the other forces. It's much weaker, it affects everything with mass or energy, and unlike the other forces, it can't be shielded or blocked. Einstein showed us that gravity isn't really a force at all, but the curvature of space-time itself. That makes it very difficult to fit into the same mathematical framework as the other forces. This is where string theory offers something genuinely revolutionary. In string theory, all four fundamental forces arise from the same basic phenomenon: vibrating strings. Different vibration patterns of the same fundamental strings would give rise to the particles that carry each of the different forces. The particle that carries electromagnetic force, the photon, would correspond to strings vibrating in one particular way. The particles that carry the strong nuclear force, called gluons, would be strings vibrating in a different pattern. The W and Z bosons that carry the weak nuclear force would represent yet other vibration modes of the fundamental strings. And gravity? In string theory, gravity would be carried by a particle called the graviton, which would correspond to strings vibrating in a very specific way, as closed loops rather than open strings. This difference might explain why gravity seems so different from the other forces. It's not that gravity is fundamentally different, it's just that its corresponding strings have a different topology, a different shape. This would mean that the four fundamental forces aren't really four different things at all. They would be four different melodies played by the same cosmic instrument. The universe wouldn't be like four separate orchestras, but like a single, incredibly complex symphony where different sections play different themes that combine to create the rich tapestry of physical reality. But string theory goes even further than just unifying the forces. It suggests that forces and matter, the vibrations that create force-carrying particles and the vibrations that create matter particles, are just different aspects of the same underlying string dynamics. In other words, the distinction between the stuff of reality and the forces that govern it might itself be an illusion. Everything, both matter and force, would emerge from the same basic phenomenon: strings vibrating in the fundamental fabric of space-time. This leads to one of the most beautiful aspects of string theory, its mathematical consistency. Unlike other attempts to unify the forces, string theory doesn't require physicists to force different mathematical frameworks together like mismatched puzzle pieces. Instead, the unification emerges naturally from the mathematics of vibrating strings in higher dimensional space. The theory predicts that at extremely high energies that existed only in the very first moments after the Big Bang, all the forces would indeed merge into one. As the universe cooled and expanded, this single, unified force would have broken apart, like light splitting into different colors through a prism, giving rise to the four distinct forces we observe today. There's something deeply satisfying about this picture. It suggests that beneath all the apparent complexity and diversity of the physical world, there might be a profound simplicity. The electromagnetic force that powers your phone, the gravity that holds planets in orbit, the nuclear forces that make stars shine, would all be variations on the same theme, different voices singing different parts of the same cosmic song. Of course, proving that this beautiful mathematical picture corresponds to reality remains one of the great challenges in physics. The energies required to see the forces unify are far beyond anything we can create in laboratory experiments. We can only look for indirect evidence, subtle signatures that might confirm or contradict string theory's predictions. But the possibility alone changes how we might think about the forces that shape our world. Every time you flip a light switch, every time you feel the pull of gravity, every time you breathe air held together by chemical bonds, you might be experiencing different facets of the same underlying reality. The music of vibrating strings resonating through the hidden dimensions of space. At the smallest scales imaginable, reality starts to behave like a jazz improvisation where the notes change every time you listen. Quantum mechanics has always been the strange cousin in the family of physics theories. Unlike the predictable, clockwork universe of classical physics, the quantum world is fundamentally uncertain. Particles don't have definite positions or speeds until you measure them. They can exist in multiple states simultaneously, be in two places at once, or tunnel through barriers that should be impossible to cross. This isn't just a limitation of our measurement techniques or a sign that our theories are incomplete. The uncertainty is built into the very fabric of reality at the smallest scales. It's as if the universe itself is constantly improvising, making choices about what to be only when forced to by observation or interaction. For decades, physicists have struggled to understand how this quantum weirdness fits together with our theories of space and time. In quantum mechanics, you can have particles popping into existence out of nothing, borrowing energy from the vacuum as long as they pay it back quickly enough. Virtual particles flicker in and out of existence, creating a kind of quantum foam at the smallest scales of space and time. String theory offers a fascinating new perspective on these quantum mysteries. Instead of thinking about point particles dancing their quantum dance, string theory asks us to imagine tiny loops and segments of energy vibrating their way through space and time. And this simple change in perspective leads to some remarkable consequences. One of the most striking things about strings is that they're extended objects, not mathematical points. A typical string might be incredibly small, but it still has length, however tiny. This means that unlike point particles, which can approach each other arbitrarily closely and create mathematical infinities, strings have a natural minimum size scale. They can only get so close to each other before their stringy nature becomes important. This extended structure helps resolve some of the infinities that plague other quantum theories. When physicists try to calculate what happens when point particles interact, they often get infinite answers, meaningless results that have to be artificially removed through complex mathematical procedures. But string interactions are naturally finite because strings can't collapse to zero size the way point particles can. Think of it like the difference between trying to balance two sharp needles point to point versus trying to balance two guitar strings. The needles can theoretically touch at a single mathematical point, creating an unstable, infinite energy situation. The guitar strings, being extended objects, interact over their entire length, creating a more stable, well-defined interaction. String theory also offers a new way to understand the quantum uncertainty that permeates the microscopic world. In traditional quantum mechanics, uncertainty arises because particles don't have definite properties until measured. In string theory, this uncertainty might reflect the fact that strings are constantly vibrating, constantly changing their configuration in subtle ways. Imagine trying to photograph a vibrating guitar string. Even with the fastest camera, you'd never capture the string at rest. It would always be in motion, blurred across multiple positions. Similarly, the properties of fundamental particles might be blurred because the underlying strings are never at rest, always vibrating between different configurations. But string theory's approach to quantum mechanics goes deeper than just providing a new metaphor. The mathematics of string theory naturally incorporates quantum principles in a way that seems more elegant and self-consistent than previous approaches. For instance, string theory requires the existence of supersymmetry, a deep symmetry that connects particles of different types. In a supersymmetric theory, every particle has a partner particle with slightly different properties. These partnerships help stabilize the quantum fluctuations that otherwise tend to run wild in theories of quantum gravity. The theory also suggests that the quantum foam, the bubbling uncertainty at the smallest scales of space and time, might actually be composed of tiny strings splitting and joining. Instead of particles popping in and out of existence, we would have strings dividing like cellular mitosis or joining together like cosmic marriages. The quantum dance becomes a string dance, more like a flowing, continuous choreography than the abrupt appearances and disappearances of point particles. One of the most beautiful aspects of string theory's approach to quantum mechanics is how it handles the measurement problem, the question of how and when quantum possibilities collapse into definite realities. In string theory, this collapse might be understood as strings settling into particular vibration patterns after interacting with their environment. It's as if each string interaction is like a musical conversation. Before the interaction, each string might be vibrating in a superposition of different modes, like a chord with multiple notes playing simultaneously. The interaction between strings would be like a musical dialogue where the different possible notes influence each other until they settle into a harmonious resolution. This picture suggests that quantum uncertainty isn't just a mysterious feature of nature that we have to accept, but a natural consequence of the underlying musical structure of reality. The universe improvises because it's literally made of music, and music, by its very nature, flows and changes and creates new harmonies through the interaction of different voices. Of course, all of this remains highly theoretical. We don't yet have experimental evidence for the existence of strings, and the mathematical machinery required to make precise predictions from string theory is extraordinarily complex. But the framework offers a compelling new way to think about the quantum nature of reality. As you settle into sleep, your brain activity slowing, your thoughts becoming softer and less defined, you might imagine that you're participating in the quantum dance yourself. Every atom in your body, every chemical reaction in your cells, every electrical impulse in your neurons would be part of this vast improvisation, this cosmic jazz session where tiny strings vibrate their way through the hidden dimensions of space and time, creating the music that is you. Gravity has always been the odd one out, like that friend who shows up to parties but never quite fits in with the group. While the other three fundamental forces, electromagnetic, strong nuclear, and weak nuclear, all play by quantum mechanical rules, gravity seems to march to the beat of its own drummer. Einstein showed us that gravity isn't really a force at all, but the curvature of spacetime itself. Massive objects like stars and planets warp the fabric of space and time around them, and what we experience as gravitational attraction is really just objects following the curves in this warped spacetime. It's a beautiful and elegant picture, and it works wonderfully for describing everything from falling apples to orbiting planets to the expansion of the entire universe. But when physicists try to apply quantum mechanics to gravity, everything breaks down. The problem becomes apparent when you try to describe what happens at the smallest scales, where both gravity and quantum effects should be important. Consider the interior of a black hole, where matter is compressed to infinite density according to Einstein's equations. Or think about the very first moment of the Big Bang, when all the matter and energy in the observable universe was packed into a volume smaller than a proton. In these extreme conditions, you can't ignore quantum mechanics. The uncertainty principle tells us that at very small scales, space and time themselves should start to fluctuate wildly. Virtual particles should pop in and out of existence, borrowing energy from the vacuum and paying it back in quantum timescales. But these quantum fluctuations would create gravitational effects, which would in turn influence the quantum fluctuations, creating a runaway feedback loop that makes the mathematics explode into meaningless infinities. It's like trying to tune a guitar while someone is shaking the tuning pegs. Every adjustment you make gets amplified and distorted by the shaking, making it impossible to find a stable, harmonious state. For decades, physicists tried various approaches to solve this problem. They attempted to apply the same techniques that had successfully merged quantum mechanics with electromagnetism, but gravity proved stubbornly resistant to these methods. Part of the difficulty is that gravity is so much weaker than the other forces, but it's also universal. Everything with mass or energy creates and responds to gravitational fields. String theory offers what might be the first truly successful approach to quantum gravity. The key insight is that gravity, in string theory, isn't treated as something fundamentally different from the other forces. Instead, it emerges naturally from the vibrations of closed strings. In string theory, the particle that would carry the gravitational force is called the graviton. Unlike the particles that carry the other forces, which correspond to open strings with two free ends, the graviton corresponds to a closed string, a loop with no ends at all. This difference in topology, this difference in shape, might be why gravity behaves so differently from the other forces. Closed strings can vibrate in ways that open strings cannot. They can twist, they can change size, they can oscillate in complex patterns that span all the dimensions of space, including the hidden ones. When a closed string vibrates in its lowest energy mode, its simplest pattern, the result looks exactly like what we would expect from a graviton, a massless particle that couples to energy and momentum in precisely the way that Einstein's theory predicts. But string theory goes further than just providing a quantum description of individual gravitons. It offers a complete framework for understanding how spacetime itself emerges from string dynamics. In this picture, the smooth, continuous spacetime of Einstein's relativity would be an approximation, valid at large scales, but breaking down when you zoom in far enough to see the underlying string structure. Imagine looking at a photograph from far away. From a distance, it appears to be a smooth, continuous image. But if you look closely enough, you can see that it's actually made up of discrete pixels, tiny dots of different colors that combine to create the illusion of smoothness. String theory suggests that spacetime might be similar, apparently smooth and continuous at the scales we normally experience, but actually composed of something more fundamental when examined at the smallest possible scales. This pixelated view of spacetime helps resolve many of the problems that plague other approaches to quantum gravity. The infinities that arise when point particles interact in curved spacetime are naturally cut off at the string scale. Instead of trying to make sense of physics at arbitrarily small distances, string theory suggests that there's a minimum meaningful size, a resolution limit below which the very concept of distance breaks down. String theory also provides a natural explanation for why gravity is so much weaker than the other forces. In the framework of extra dimensions, gravity might be the only force that can spread out into all the dimensions of space. While electromagnetic and nuclear forces are confined to our familiar three-dimensional world, gravity permeates all the dimensions, including the hidden ones. This dilution effect would make gravity appear much weaker than it actually is, like sound spreading out in all directions and becoming fainter with distance. Perhaps most remarkably, string theory suggests that the relationship between gravity and quantum mechanics isn't one of conflict, but of deep complementarity. The quantum uncertainties that seem to destroy the smooth spacetime of relativity might actually be the very thing that creates spacetime in the first place. It's a picture where reality emerges from music, where the vibrations of fundamental strings create not just particles and forces, but space and time themselves. Gravity wouldn't be the odd one out anymore, but would be part of the same cosmic symphony, played by closed strings vibrating through the hidden dimensions of a universe far stranger and more musical than we ever imagined. The mathematics is still being worked out, and experimental confirmation remains elusive. But for the first time, physicists have a framework that might actually solve the gravity problem, not by forcing quantum mechanics and relativity to coexist, but by showing that they're both aspects of something even more fundamental, the music of vibrating strings resonating through the fabric of reality itself. Some strings have ends that wiggle freely, while others form perfect loops, like cosmic rubber bands with no beginning or end. In the world of string theory, topology, the study of shapes and connections becomes as important as the more familiar concepts of mass and energy. The difference between a string with two free ends and a string that closes in on itself to form a perfect loop might seem like a minor detail, but it leads to profound consequences for the kinds of particles and forces that emerge from string vibrations. Open strings are perhaps easier to visualize. Picture a tiny segment of thread, so small it would make an atom look like a planet, floating freely in space. Both ends of this thread can vibrate independently, wiggling back and forth like the ends of a jump rope. These vibrations propagate along the length of the string, creating standing wave patterns that determine what kind of particle the string appears to be. The key feature of open strings is that their endpoints are free to move, but they can't just move anywhere. In most versions of string theory, the endpoints of open strings are confined to what physicists call D-branes, higher dimensional surfaces that act like cosmic membranes. Think of D-branes as vast, thin sheets stretched through space, possibly extending through some of the extra dimensions that string theory requires. Our familiar three-dimensional world might actually be one of these D-branes, a three-dimensional surface embedded in a higher dimensional space. The endpoints of open strings would be stuck to our brain like flies stuck to flypaper, able to slide around on the surface but unable to leave it entirely. This confinement might explain why we observe particles moving through three-dimensional space, but not through the additional dimensions that string theory predicts. The vibrations of open strings give rise to many of the particles we know and love. Electrons, quarks, photons, all the building blocks of atoms and light could be different vibrational modes of open strings. Each different pattern of vibration, each different standing wave along the string's length would correspond to a particle with different properties, different mass, different electric charge, different behavior. But open strings have limitations. Because their endpoints are confined to D-branes, the forces they create are also confined. Electromagnetic forces, nuclear forces, all the interactions between matter particles would be restricted to the same three-dimensional brane that we inhabit. They couldn't spread out into the additional dimensions of space. Closed strings are different. With no endpoints to confine them, closed strings are free to move through all the dimensions of space, including the hidden ones that we can't directly perceive. They're like cosmic hula hoops, free to rotate and vibrate in ways that open strings cannot. The lowest energy vibration mode of a closed string produces what string theorists call a graviton, the hypothetical particle that carries the gravitational force. Unlike the particles produced by open strings, gravitons are free to propagate through all the dimensions of space. This freedom might explain why gravity is so much weaker than the other forces. It's not confined to our three-dimensional brain, but spreads out through the additional dimensions, becoming diluted in the process. Imagine shouting in a narrow hallway versus shouting in a vast cathedral. In the hallway, all the sound energy is concentrated in a small space, so your voice seems loud and clear. In the cathedral, the same amount of sound energy spreads out in all directions, making your voice seem much fainter. Gravity might be like the voice in the cathedral, spreading through dimensions we can't perceive and becoming weaker as a result. Closed strings can also vibrate in more complex ways than open strings. They can twist, they can change their size, they can oscillate in patterns that have no equivalent in open string vibrations. Some of these vibration modes might correspond to particles and fields that we haven't discovered yet. exotic forms of matter and energy that interact so weakly with ordinary matter that they've escaped detection. The distinction between open and closed strings also has implications for the structure of spacetime itself. Open strings, confined to D-branes, interact primarily with the geometry of those branes. But closed strings interact with the geometry of all of space, including the hidden dimensions. The vibrations of closed strings might actually determine the shape and size of the extra dimensions, dynamically adjusting the geometry of space in response to the matter and energy present. This leads to one of the most intriguing possibilities in string theory, that the familiar three-dimensional space we inhabit might not be fundamental, but emergent. Our brain might be like the surface of a lake, a two-dimensional interface between air and water that emerges from the interactions of the three-dimensional fluids above and below. Similarly, our three-dimensional world might emerge from the interactions of strings in higher dimensional space. Some versions of string theory even suggest that open and closed strings can transform into one another under certain conditions. An open string might close up into a loop, or a closed string might break apart into two open strings. These transformations would correspond to processes where matter particles on our brain could disappear into the higher dimensional bulk space, or where new particles could appear seemingly from nothing as closed strings from the bulk space break apart on our brain. The mathematics of these processes is extremely complex, involving concepts from advanced geometry and topology that push the boundaries of current mathematical knowledge. But the basic picture is elegantly simple. Reality emerges from the interplay between two kinds of cosmic music: the confined melodies of open strings playing on the surface of three-dimensional branes, and the free-flowing harmonies of closed strings resonating through all the dimensions of space. Whether this picture corresponds to reality remains an open question. We have no direct evidence for the existence of D-branes, extra dimensions, or the strings themselves. But the mathematical consistency and elegance of the framework continues to attract physicists and mathematicians, offering hope that the fundamental nature of reality might be far more musical and interconnected than our everyday experience suggests. As you drift towards sleep, your consciousness settling like ripples on a pond, you might imagine yourself as part of this cosmic string ensemble, your thoughts and dreams emerging from the gentle vibrations of open strings confined to our three-dimensional brain, while gravity and space-time itself flow from the deeper harmonies of closed strings dancing through dimensions beyond perception. What if our universe is just one bubble in an endless bath, floating alongside countless others we'll never see? String theory doesn't just suggest that our universe might be made of vibrating strings. It implies something far more extraordinary, that our universe might be just one of an infinite number of possible universes, each with its own laws of physics, its own particles, its own story. This idea emerges naturally from the mathematics of string theory, though it's one of the most difficult concepts to wrap our minds around. Remember that in string theory, the properties of particles and forces depend on how the extra dimensions are curled up and folded. But there isn't just one way to fold up 6 extra dimensions into tiny, hidden shapes. There are many ways, perhaps infinitely many ways. Each different way of folding the extra dimensions would create a universe with different physics. In one universe, electrons might be heavier or lighter. In another, the force of gravity might be stronger or weaker. In yet another, there might be entirely different particles that don't exist in our reality. The mathematical landscape of possibilities is so vast that physicists call it simply the landscape, a terrain of potential realities stretching beyond the horizon of imagination. Think of it like a vast garden where every flower represents a different possible universe. Some flowers might be very similar to each other, like neighboring universes where the only difference is the mass of a single particle. Others might be wildly different, with completely different organizing principles, different numbers of forces, different ways of structuring matter and energy. Our universe would be just one flower in this infinite garden, special to us because it's the only one we can see, but not necessarily unique or privileged in any objective sense. We exist in this particular universe not because it's the correct one, but because it's the one that allows for the existence of stars, planets, chemistry, and life. In universes where the forces are too strong or too weak, where particles can't form stable atoms, or where spacetime itself is unstable, there would be no observers to wonder about the nature of reality. This selection effect is sometimes called the anthropic principle. We observe the physical constants and laws that we do not because they're the only possible values, but because they're among the values that allow for observers to exist. It's like asking why all the people in a photograph are smiling and concluding that all humans must be happy all the time, when really you're just looking at a wedding photo where people were specifically arranged to smile. But the multiverse of string theory goes beyond just different values for familiar physical constants. In some regions of this landscape, the very structure of reality might be different. There might be universes where space has different numbers of dimensions, where time flows differently, where the basic categories of matter and energy don't apply. Some physicists find this proliferation of possibilities troubling. If string theory predicts that almost anything is possible somewhere in the multiverse, then it doesn't really predict anything specific about our universe. It becomes less like a theory that explains why things are the way they are, and more like a framework that accommodates any possible observation. Others find the multiverse idea liberating. It suggests that the apparent fine-tuning of physical constants that allows for the existence of complexity and life isn't evidence for cosmic design, but a natural consequence of selection effects in an infinite landscape of possibilities. We exist in a universe suitable for life because universes unsuitable for life don't produce observers to comment on their unsuitability. The multiverse also offers a potential explanation for some of the puzzling features of quantum mechanics. In our discussion of quantum uncertainty, we saw how particles seem to exist in multiple states simultaneously until observed. In a multiverse interpretation, these multiple states might correspond to the particle actually existing in different states in different universe branches. What we interpret as quantum uncertainty might be our limited perspective on a reality that includes all possible outcomes. But perhaps the most profound implication of the multiverse is what it suggests about the nature of existence itself. If every mathematically consistent possibility is realized somewhere in the landscape, then reality becomes not a single story, but an infinite library containing every possible story. Every decision not made, every path not taken, every alternative history would exist somewhere in the vast space of possibilities. This doesn't mean that all universes are equally probable, or that we could ever visit or communicate with other branches of the multiverse. The different universe bubbles would be causally disconnected from each other, separated by regions of space and time that expand faster than light can travel between them. Each universe would be an island of reality in an infinite sea of possibilities. There's something both humbling and comforting about this picture. Humbling because it suggests that our entire observable universe, with its billions of galaxies and trillions of stars, might be just one tiny bubble in an inconceivably vast foam of realities. Comforting because it suggests that every possibility, every potential for beauty and complexity and meaning is realized somewhere in the full scope of existence. String theory doesn't definitively predict that the multiverse exists, The mathematics allows for it, but proving that other universes actually exist, rather than just being mathematical possibilities, remains one of the deepest challenges in theoretical physics. By definition, we can only observe our own universe, so evidence for other universes must be indirect, subtle signatures in the cosmic microwave background radiation or other observable phenomena. But the very fact that our most sophisticated theories naturally lead us to contemplate infinite gardens of reality suggests that the universe, or multiverse, might be far stranger and more abundant than our ancestors ever dreamed. As you settle into sleep and let your consciousness explore the landscape of dreams, you might imagine yourself floating through this vast garden of possibilities, each dream a glimpse of what reality might be like in some distant branch of the infinite tree of existence. 6 extra dimensions might be curled up inside every point in space, smaller than the smallest thing you can imagine. We've touched on the idea of extra dimensions before, but it's worth taking a gentle, closer look at just how strange and wonderful this concept really is. If string theory is correct, then every point in the space around you, every location where you could place your fingertip, isn't really a simple point at all. It's a tiny, incredibly complex 6-dimensional shape, folded and twisted in ways that make origami look like child's play. These shapes have names that sound like they belong in a fantasy novel. Calabi-Yao manifolds, named after mathematicians Eugenio Calabi and Tung Yao, who studied their mathematical properties decades before anyone thought they might be relevant to physics. But despite their exotic names, these geometries might be the most fundamental aspect of reality, the hidden architecture that determines why the universe works the way it does. To get a sense of how dimensions can hide, let's start with a simpler example. Imagine you're looking at a basketball from across a gymnasium. From that distance, the ball appears to be a perfect sphere, a simple 3-dimensional object. But if you could zoom in with incredible magnification, you'd see that the surface isn't smooth at all. It has texture, tiny bumps and valleys that create the grip patterns basketball players rely on. Zoom in further and you'd see the molecular structure of the rubber, a complex 3-dimensional network invisible from a distance. In string theory, something similar is happening with space itself, but the hidden structure exists in additional dimensions rather than just fine-scale detail in familiar dimensions. Every point in our 3-dimensional space is like that basketball, apparently simple from our perspective, but actually possessing an intricate internal structure that extends into dimensions we can't directly perceive. But why 6 extra dimensions specifically? The answer comes from the mathematical requirements of string theory. For the theory to be mathematically consistent, to avoid the infinities and contradictions that plague other approaches, the total number of spatial dimensions must be precisely 9. We experience 3 of these dimensions directly, so that leaves 6 dimensions that must somehow be hidden from our everyday experience. These 6 dimensions can't just be rolled up randomly. They must be folded according to very specific mathematical rules to preserve the symmetries that string theory requires. The resulting shapes, the Calabi-Yao manifolds, are solutions to complex geometric equations, 6-dimensional sculptures that exist in the mathematical realm of topology and differential geometry. Trying to visualize a 6-dimensional shape is essentially impossible for our 3-dimensional brains, but mathematicians have found ways to represent pieces of these structures in forms we can somewhat comprehend. Imagine starting with a sphere, then adding handles to connect different parts of the surface, then adding more complex structures like holes that tunnel through the shape in various directions. Now imagine doing this not in 3 dimensions but in 6, with connections and tunnels that can twist through dimensions we can't picture. The resulting shape might have hundreds or thousands of holes, tunnels, and connections, all packed into a space so small it makes atoms look enormous. But these aren't just abstract mathematical curiosities. In string theory, the specific shape of the Calabi-Yao manifold at each point in space determines the physics we observe. The way strings vibrate depends on the geometry they're vibrating through, just as the sound of a musical instrument depends on its shape and internal structure. Different types of holes and connections in the manifold correspond to different particles and forces. A manifold with certain types of tunnels might allow for particles with particular masses and charges. A manifold with different geometric features might produce a completely different spectrum of particles. The six-dimensional shape acts like a cosmic instrument, and the strings vibrating through it create the music we observe as physical reality. This leads to one of the most remarkable implications of hidden dimensions: the possibility that different regions of space might have slightly different six-dimensional geometries, leading to slowly varying physical constants. What we think of as the immutable laws of physics might actually be the local properties of our particular region of the higher dimensional landscape. The compactification of extra dimensions also offers potential explanations for some of the deepest mysteries in physics. Why do particles have the masses they do? Why are the forces exactly as strong as they are? Why does space have 3 dimensions instead of 2 or 4 or 17? All of these questions might have answers that involve the specific 6-dimensional geometry folded up at every point in space. There's also the tantalizing possibility that these hidden dimensions might not be completely static. They might slowly evolve over cosmic time, gradually changing shape as the universe expands and cools. This evolution could lead to slow changes in physical constants, effects so gradual that they would be difficult to detect, but that might leave subtle signatures in the cosmic microwave background radiation or in the light from distant galaxies. Some versions of string theory even allow for the possibility that the extra dimensions might be larger than we think, with consequences that could be detectable in high-energy particle collisions. If particles can access these larger extra dimensions, they might appear to disappear from our 3-dimensional world, carrying energy and momentum into the hidden directions of space. The mathematics of Calabi-Yao manifolds is so complex that even with modern computers, physicists have only been able to study a few thousand of the potentially infinite number of possible 6-dimensional geometries. Each one corresponds to a different possible physics, a different way the universe could work. Our particular geometry, the one that produces the particles and forces we observe, is just one point in this vast landscape of mathematical possibilities. As you rest and let your mind wander towards sleep, you might imagine these hidden dimensions folded up inside every atom of your body, tiny 6-dimensional gardens more complex than the most intricate cathedral, all nested within spaces smaller than the smallest things you can conceive. Every breath you take, every thought you think, emerges from strings vibrating through these invisible geometries, creating the reality you experience from a music played in dimensions beyond perception. Every particle you know might have a secret twin, a shadow partner dancing just out of sight. One of the most elegant and mysterious predictions of string theory is that every particle in the universe should have a partner, a shadow twin with properties that mirror and complement its own. This idea is called supersymmetry, and it suggests that the fundamental structure of reality is even more intricate and balanced than we ever imagined. To understand supersymmetry, it helps to think about the 2 basic categories of particles that exist in nature. There are particles like electrons and quarks, which make up matter and have a property called half-integer spin. These are called fermions, after physicist Enrico Fermi. Then there are particles like photons and the theoretical graviton, which carry forces and have integer spin. These are called bosons, after physicist Satyendra Nath Bose. Fermions and bosons behave very differently. Fermions are loners. They obey the Pauli exclusion principle, which means that no two identical fermions can occupy the same quantum state. This antisocial behavior is actually what gives matter its structure and solidity. Electrons in atoms, for instance, are forced to occupy different energy levels because they can't all crowd into the same state. Bosons, on the other hand, are gregarious. They love to bunch up together in the same quantum state. This is what allows for phenomena like laser light, where billions of photons march in perfect synchronization, all doing exactly the same thing. Supersymmetry proposes that for every fermion in nature, there's a corresponding boson, and vice versa. Every matter particle would have a force-carrying partner, and every force-carrying particle would have a matter-like twin. The electron would have a partner called the selectron. The photon would have a partner called the photino. Quarks would have squark partners, neutrinos would have neutrino partners, and so on. These supersymmetric partners would be like quantum mechanical dance partners, forever linked by the deep symmetries that govern the universe. But here's the puzzling part. If every particle has a supersymmetric partner, where are they? We've never observed a selectron or a photino or any of the other predicted superpartners. The answer, according to supersymmetric theory, is that supersymmetry is broken in our current universe. This doesn't mean the symmetry doesn't exist, but rather that the conditions of our low-energy, cool universe hide the symmetry from direct observation. It's like looking at your reflection in a funhouse mirror. The fundamental symmetry between you and your reflection is still there, but it's been distorted by the curved surface of the mirror. In the early universe, when temperatures and energies were much higher, supersymmetry might have been unbroken, with particles and their superpartners having identical masses and properties. But as the universe cooled and expanded, something happened to break this symmetry, making the superpartners much heavier than their ordinary counterparts and therefore unstable, decaying quickly into lighter, more familiar particles. This breaking of supersymmetry is actually essential for explaining why our universe looks the way it does. If supersymmetry were unbroken, every electron would be accompanied by its selectron partner, every photon by its photino partner. The universe would be a very different place, possibly one where stable atoms and chemistry couldn't exist. But even though supersymmetry appears to be broken in our low-energy world, it still plays a crucial role in string theory. In fact, string theory seems to require supersymmetry to be mathematically consistent. Without it, the theory produces particles with negative mass squared, tachyons that would make the universe unstable and causality violating. Supersymmetry also helps solve some of the technical problems that arise when trying to unify quantum mechanics with gravity. The quantum fluctuations that normally destroy the smooth spacetime of general relativity are tamed by the presence of supersymmetric partners. Fermion loops and boson loops in quantum calculations tend to cancel each other out when supersymmetry is present, leading to finite, well-behaved results, instead of the infinities that plague other theories. There's something deeply beautiful about the idea of supersymmetry. It suggests that the universe has an underlying balance, a cosmic yin and yang, where every type of particle is paired with its complementary opposite. Matter particles are balanced by force particles. Particles with half-integer spin are balanced by particles with integer spin. And the quantum fluctuations that could destroy reality are tamed by the presence of these shadow partners. But supersymmetry remains one of the great unconfirmed predictions of theoretical physics. Despite decades of searching in particle accelerators, scientists have found no evidence for selectrons, photinos, or any of the other predicted superpartners. This doesn't necessarily mean supersymmetry is wrong, but it does suggest that if it exists, the superpartners are heavier than current technology can produce, hiding just beyond the energy frontier of our most powerful experiments. Some physicists remain optimistic that supersymmetric particles will be discovered as accelerators become more powerful. Others worry that if supersymmetry exists at all, it might be broken so severely that the superpartners are too heavy to ever be produced in laboratory experiments. The particles might exist in principle but remain forever beyond our experimental reach. There's also the intriguing possibility that some of the mysterious dark matter that makes up most of the universe's mass might actually be composed of supersymmetric particles. The lightest supersymmetric particle, if it exists and is stable, would be an ideal candidate for dark matter. It would interact very weakly with ordinary matter, making it invisible to telescopes but detectable through its gravitational effects. The mathematics of supersymmetry is extraordinarily elegant, connecting the geometry of space and time with the properties of quantum fields in ways that seem almost too beautiful to be accidental. Whether this mathematical beauty reflects a deep truth about nature or is simply an artifact of our theoretical constructions remains one of the great open questions in physics. As you settle into the quiet rhythms of approaching sleep, you might imagine this hidden mirror world of supersymmetric particles, shadow twins of every atom in your body, every photon of light, every quantum field that permeates space. They would be there but not there, real but unobservable, partners in a cosmic dance that maintains the balance and stability of reality itself. In the deepest mathematical sense, you would never be alone, always accompanied by your invisible supersymmetric shadow, a quantum reflection dancing through dimensions beyond perception. The strangest idea in string theory isn't about tiny strings or hidden dimensions, it's that everything you experience might be a projection. Imagine you're looking at a hologram, one of those shimmery images that appears three-dimensional even though it's actually encoded on a flat, two-dimensional surface. Move your head, and the image shifts perspective as if you were looking at a real three-dimensional object. Yet all the information that creates this illusion of depth and volume is somehow contained in the flat surface of the hologram itself. Now imagine something far more radical. What if the entire three-dimensional universe you experience, with all its depth and volume, all its space for stars and galaxies, and the room you're sitting in, is actually a projection from information encoded on a distant two-dimensional surface? This isn't science fiction or philosophical speculation. It's one of the most serious and revolutionary ideas to emerge from string theory, and it's called the holographic principle. The idea began with the study of black holes, those mysterious objects where gravity is so strong that not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery about black holes. Their entropy, a measure of the amount of information they contain, is proportional not to their volume, but to the area of their surface. This was completely unexpected, like finding that the amount of information in a library depends on the size of its walls rather than the number of books it contains. Stephen Hawking's subsequent work on black hole radiation deepened the mystery. He showed that black holes aren't completely black, but actually emit a faint glow of radiation. As they radiate, they slowly evaporate, and the information that falls into them seems to disappear forever. But quantum mechanics says that information can never be completely destroyed, leading to what became known as the black hole information paradox. String theory offered a potential resolution to this paradox through the holographic principle. The idea is that all the information that appears to be contained within the three-dimensional volume of a black hole is actually encoded on its two-dimensional boundary, its event horizon. The three-dimensional interior would be a kind of projection, a holographic reconstruction of information stored on the surface. But the implications of this idea extend far beyond black holes. If the principle works for black holes, why not for the entire universe? Perhaps all of three-dimensional space, everything you see and touch and move through, is actually a holographic projection from information encoded on a distant two-dimensional boundary. This boundary would be unimaginably far away, at the edge of the observable universe or beyond. The information encoded there would contain a complete description of everything that happens within the three-dimensional volume, every particle interaction, every thought you think, every star that shines. What you experience as three-dimensional reality would be a kind of cosmic hologram, a projection that creates the illusion of depth and volume from information stored on a flat surface. The mathematics of this holographic correspondence has been worked out in remarkable detail for certain simplified universes. Physicists have found exact mathematical relationships between physics in three-dimensional space and physics on a two-dimensional boundary. Every particle, every force, every quantum field in the three-dimensional interior corresponds to something specific on the two-dimensional surface. This correspondence is so precise that it's led to a new way of thinking about the fundamental nature of space and time. Instead of three-dimensional space being primary with its boundary as a derived concept, the holographic principle suggests the opposite. The two-dimensional boundary is fundamental, and three-dimensional space is emergent, a useful illusion created by the holographic projection. Think of it like watching a movie. The movie appears to take place in a three-dimensional world with characters moving through space and time. But the fundamental reality is the two-dimensional screen and the pattern of light and dark pixels that create the illusion of depth and motion. The three-dimensional world of the movie is real in the sense that it can affect you emotionally and intellectually, but it's not fundamental in the same way that the screen is. The holographic principle also offers new insights into the nature of quantum entanglement, the spooky connection between particles that Einstein found so troubling. In the holographic description, particles that appear entangled in the three-dimensional interior correspond to connected regions on the two-dimensional boundary. The mysterious quantum correlations that seem to violate locality might actually reflect the geometry of the holographic encoding. There's something both unsettling and beautiful about this picture. Unsettling because it suggests that your direct experience of three-dimensional space might be fundamentally illusory, that the depth and volume you feel so certain about is actually a projection from a flat surface you can never reach or directly observe. Beautiful because it reveals a deep unity between seemingly different descriptions of reality, showing that the same underlying information can manifest in radically different ways. The holographic principle also has practical applications in theoretical physics. The mathematical techniques developed to understand holographic correspondences have led to new insights into strongly correlated quantum systems, materials where quantum effects produce behavior that can't be understood using traditional methods. The holographic dictionary allows physicists to translate difficult problems in three-dimensional physics into more tractable problems in two dimensions. But perhaps the most profound implication of the holographic principle is what it suggests about the nature of information and reality. If everything you experience is ultimately information encoded on a distant surface, then information becomes more fundamental than space, time, matter, or energy. Reality would be, in the deepest sense, informational rather than material. This informational view of reality connects to some of the deepest questions in physics and philosophy. What is consciousness? How does subjective experience arise from objective physical processes? If reality is fundamentally information, then consciousness might be understood as a particular way that information processes and experiences itself. As you drift towards sleep, your consciousness gradually releasing its grip on three-dimensional experience. You might imagine yourself as both the projection and the projected, both the information encoded on some distant cosmic boundary and the three-dimensional experience that emerges from that encoding. In dreams, the normal rules of space and time already become fluid and negotiable. Perhaps sleep offers a glimpse of what reality might be like if we could step outside the holographic projection and see the universe from the perspective of the encoding boundary itself. Not everyone is convinced that the universe is made of music, and they have some pretty good reasons for their doubts. String theory is undeniably beautiful. Its mathematics is elegant, its unifying vision is compelling, and its potential to resolve some of the deepest puzzles in physics is genuine. But beauty alone doesn't make a theory correct, and string theory has attracted serious criticism from thoughtful physicists who question whether it deserves its status as the leading candidate for a theory of everything. The most fundamental criticism is that string theory has yet to make a single testable prediction that distinguishes it from other theories. In science, theories are ultimately judged not by their mathematical elegance, but by their ability to make predictions that can be confirmed or contradicted by experiment. Einstein's theory of relativity, for instance, predicted that light would bend around massive objects, that clocks would run slower in gravitational fields, and that gravitational waves would ripple through spacetime. These predictions were eventually confirmed by observation, providing strong evidence that the theory describes reality. String theory, despite decades of development, has struggled to make similar, clear, testable predictions. The energy scales where stringy effects would become apparent are so high that they existed only in the first moments after the Big Bang. The extra dimensions are supposedly so small that they're far beyond the reach of any conceivable experiment. The supersymmetric particles that the theory predicts remain stubbornly absent from particle accelerator data. Critics argue that without testable predictions, string theory isn't really a scientific theory at all, but rather a mathematical framework or research program. It may be interesting and intellectually stimulating, but it doesn't meet the basic criterion that distinguishes science from mathematics, the ability to be proven wrong by observation. Another major criticism involves what's called the landscape problem. We've talked about how different ways of compactifying the extra dimensions lead to different possible universes with different physics. But the number of possible compactifications is enormous, possibly infinite. Some estimates suggest there might be 10 to the 500th power different ways to fold up the extra dimensions, each corresponding to a different possible universe. This vast multiplicity of possibilities makes it virtually impossible to extract specific predictions from string theory. If almost any conceivable physics can be realized somewhere in the string landscape, then the theory doesn't really predict anything specific about our particular universe. It's like a theory that predicts the outcome of every possible coin flip by saying that somewhere in the multiverse, every possible sequence of heads and tails occurs. The landscape problem is sometimes called the naturalness problem. In physics, natural theories are ones where the observed values of physical constants emerge naturally from the fundamental principles without requiring special fine-tuning. But in string theory, getting a universe that looks like ours seems to require picking exactly the right compactification from an almost infinite number of possibilities. It's like finding a specific grain of sand on all the beaches in the world. Some string theorists embrace this situation, arguing that the apparent fine-tuning of physical constants is explained by the anthropic principle. We observe the constants we do because they're among the values that allow for the existence of observers. But critics find this explanation unsatisfying, arguing that it gives up on the goal of understanding why the universe is the way it is. There are also technical criticisms of string theory itself. The mathematical techniques used to study string theory often involve approximations that are valid only in certain limits. Many of the theory's most celebrated successes, like its ability to reproduce black hole entropy, rely on these approximations, and it's not always clear whether the results hold when the approximations break down. The theory also requires a number of assumptions that seem arbitrary or unmotivated. Why should the fundamental entities be one-dimensional strings rather than two-dimensional membranes or zero-dimensional points? Why should spacetime have exactly the number of dimensions that string theory requires? The answers to these questions come from the mathematical consistency of the theory, but that raises the question of whether mathematical consistency alone is sufficient reason to believe a theory describes reality. Some critics have argued that string theory has consumed too much of the theoretical physics community's attention and resources. They point out that other promising approaches to quantum gravity and unification have been relatively neglected, while vast amounts of intellectual effort have been devoted to string theory research. There's also a sociological criticism that string theory has become so dominant in certain areas of theoretical physics that it's difficult for researchers to pursue alternative approaches. Young physicists who want academic careers may feel pressured to work on string theory even if they're skeptical of its foundations. But perhaps the most serious criticism is that string theory may be unfalsifiable in principle. If the theory can accommodate almost any possible observation by invoking appropriate compactifications or multiverse considerations, then it becomes immune to experimental refutation. A theory that can't be proven wrong, critics argue, isn't a scientific theory at all. String theorists have responses to these criticisms. They point out that many successful theories in physics started as purely mathematical frameworks that took decades to make contact with experiment. They argue that the mathematical consistency requirements of string theory are so restrictive that the theory is actually highly constrained, even if those constraints don't immediately translate to testable predictions. They also emphasize that string theory has led to important advances in mathematics and has provided new insights into other areas of physics, from the behavior of materials to the dynamics of fluids. Even if string theory doesn't turn out to be the final theory of everything, they argue, it has already proven its worth as a source of new ideas and techniques. The debate between string theory supporters and critics reflects a deeper question about the nature of scientific progress. How long should the physics community continue to pursue a promising but unconfirmed theoretical approach? At what point does mathematical beauty and internal consistency become insufficient justification for continued research? These are questions without easy answers, and the debate continues to this day. As you settle into the quiet space between waking and sleeping, you might reflect on this tension between mathematical beauty and empirical validation, between the human desire for elegant explanations and the stubborn complexity of the natural world. Perhaps the ultimate test of string theory isn't whether it's beautiful or mathematically consistent, but whether it helps us better understand our place in the cosmic symphony of existence. How do you prove that invisible strings exist when they're smaller than anything we've ever measured? The challenge of testing string theory experimentally is like trying to study the fine details of a painting that's hanging on the other side of the solar system using a magnifying glass. The strings that might make up the fundamental fabric of reality are so incredibly small that they exist at what physicists call the Planck scale, a realm of distance and energy so far removed from everyday experience that it defies comprehension. To put this in perspective, if an atom was scaled up to the size of our solar system, a string would still be smaller than a human hair. The energy required to directly probe physics at the string scale would be about 1,000,000 billion times higher than what our most powerful particle accelerators can achieve. Building an accelerator capable of reaching such energies would require a machine larger than our galaxy, which is, to put it mildly, somewhat beyond current engineering capabilities. This experimental inaccessibility doesn't mean string theory is completely immune to testing, but it does mean that physicists have had to become creative about looking for indirect evidence. Instead of trying to see strings directly, researchers search for subtle signatures of stringy physics in phenomena that we can actually observe. One of the most promising avenues involves supersymmetry, string theory's prediction that every particle has a supersymmetric partner. If these superpartners exist and are light enough, they might be produced in high-energy particle collisions and detected in accelerator experiments. The Large Hadron Collider at CERN has been searching for signs of supersymmetric particles for over a decade, but so far the results have been disappointing. No clear evidence for superpartners has emerged, though this doesn't rule out their existence at higher energies that are still beyond our reach. Another approach involves looking for extra dimensions in the behavior of gravity at very small scales. In string theory, gravity can leak into the extra dimensions, potentially making it stronger than expected at microscopic distances. Precision measurements of gravitational forces between very small objects might reveal deviations from Einstein's predictions that could hint at the presence of additional spatial dimensions. Scientists have also looked for signs of extra dimensions in the products of high-energy particle collisions. If particles can access extra dimensions, some of the energy from collisions might disappear into these hidden directions of space, appearing as missing energy that doesn't balance in the collision accounts. While some intriguing anomalies have been observed, none have provided definitive evidence for extra dimensions. The study of black holes offers another potential testing ground for string theory. If string theory's description of black hole entropy and information storage is correct, it might make predictions about the radiation that black holes emit as they evaporate. Unfortunately, the black holes we can observe are so massive that they emit radiation at temperatures far too low to measure, and they would take longer than the age of the universe to evaporate significantly. But physicists have found clever ways to study black hole physics in laboratory settings. Some experiments use analog systems like sound waves in fluids or light in specially designed materials that behave mathematically like black holes. While these analog black holes can't test string theory directly, they can test some of the quantum mechanical principles that underlie string theory's approach to black hole physics. Cosmology offers perhaps the most promising arena for testing stringy ideas. The extra dimensions, vibrating strings, and complex compactifications of string theory might have left subtle imprints on the cosmic microwave background radiation, the afterglow of the Big Bang that we can observe with high precision. String theory makes predictions about the patterns of temperature fluctuations in this ancient light, and future observations might be sensitive enough to detect these signatures. The theory also predicts the existence of cosmic strings, not the fundamental strings of string theory, but extended objects that might have formed in the early universe and stretched to cosmic scales. These cosmic strings, if they exist, would gravitationally lens background light and might be detectable as characteristic patterns in surveys of distant galaxies. There's also the possibility of discovering stringy physics through the study of materials and condensed matter systems. Some of the mathematical techniques developed for string theory have found applications in understanding exotic phases of matter, and some materials exhibit behavior that can be modeled using string-like objects. While these don't test fundamental string theory directly, they demonstrate that string-like physics can emerge in complex systems. Perhaps most intriguingly, string theory has made connections to the study of quantum entanglement and information theory. The holographic principle suggests deep relationships between geometry and information, and these relationships are being tested in laboratory experiments with quantum systems. While these experiments don't prove that our universe is holographic, they do test some of the mathematical relationships that string theory predicts should exist between different descriptions of reality. The challenge of testing string theory has also driven advances in mathematical physics and computational techniques. Researchers have developed new ways to calculate physical processes, new methods for understanding the geometry of extra dimensions, and new approaches to extracting predictions from highly complex mathematical frameworks. Even if string theory ultimately proves incorrect, these techniques have found applications throughout physics and mathematics. Some physicists argue that the traditional notion of experimental testing may not apply to string theory in the same way it applies to other theories. String theory might be better understood as a mathematical framework that unifies and organizes our understanding of physics rather than a conventional theory that makes specific predictions about particular experiments. Others maintain that without experimental confirmation, string theory remains speculative, however beautiful its mathematics might be. They argue that physics is ultimately an empirical science, and theories must eventually make contact with observation to be considered scientifically valid. The search for experimental evidence of string theory continues, driven by both the desire to test one of our most sophisticated theoretical frameworks and the hope that such evidence might reveal new physics beyond our current understanding. As you drift towards sleep, imagine the scientists working through the night in laboratories around the world, sifting through data from particle collisions and telescope observations, searching for subtle clues that might reveal whether the universe really is made of music, whether reality really does emerge from the vibrations of invisible strings dancing through hidden dimensions of space and time. Sometimes, the most beautiful mathematical equations describe truths about the universe that we discover long before we understand them. There's something mysteriously compelling about mathematical beauty in physics, a quality that's hard to define but impossible to ignore when you encounter it. Physicists often talk about elegant equations, beautiful symmetries, and theories that feel right even before they're experimentally confirmed. String theory is perhaps the ultimate example of this phenomenon. A theoretical framework so mathematically rich and intricate that many of its practitioners are drawn to it as much by its beauty as by its potential to explain the universe. But what does it mean for mathematics to be beautiful? And should we trust our aesthetic sense when it comes to understanding reality? Mathematical beauty in physics often manifests as simplicity emerging from complexity, or conversely, as vast complexity arising from simple principles. Einstein's famous equation E=mc² is beautiful partly because it expresses a profound connection between matter and energy in just a few symbols. The equation seems almost too simple to contain such deep truth, yet its implications revolutionized our understanding of space, time, and the nature of reality itself. String theory exhibits a different kind of beauty, the beauty of unification and consistency. The theory doesn't just describe particles or forces or spacetime geometry in isolation. Instead, it weaves all of these phenomena together into a single mathematical framework where each element supports and constrains all the others. It's like a vast, intricate musical composition where every note is related to every other note through harmonic relationships that extend across the entire piece. The mathematical structures that appear in string theory often seem to have lives of their own, revealing unexpected connections and implications that their creators never anticipated. Calabi-Yao manifolds, the six-dimensional shapes that might describe the hidden dimensions of space, were studied by mathematicians for decades before anyone thought they might be relevant to physics. The mirror symmetry that relates different Calabi-Yao manifolds was discovered by physicists working on string theory, but it revealed deep mathematical truths that pure mathematicians had never suspected. This interplay between physics and mathematics has been one of string theory's most remarkable contributions to human knowledge. The theory has led to advances in geometry, topology, algebra, and analysis that might never have been discovered through purely mathematical research. In return, mathematical insights have illuminated new aspects of string theory and suggested new directions for research. The holographic principle, which we explored earlier, exemplifies this mathematical beauty. The idea that physics in three-dimensional space can be perfectly described by a theory on a two-dimensional boundary isn't just a curious theoretical possibility. It represents a deep mathematical duality, a way of translating between seemingly different descriptions of reality that reveals hidden simplicities in both approaches. These dualities are perhaps string theory's most beautiful feature. The theory predicts that what appears to be one kind of physics from one perspective might appear to be completely different physics from another perspective. Yet both descriptions would be equally valid and fundamentally equivalent. It's as if the same symphony could be heard as a waltz by one listener and as a tango by another, with both interpretations being completely accurate representations of the same underlying musical structure. But the relationship between mathematical beauty and physical truth is complex and sometimes misleading. History is filled with beautiful mathematical theories that turned out to have no connection to reality. There are also physical theories that work perfectly but seem mathematically ugly or inelegant. The standard model of particle physics, our most successful description of fundamental particles and forces, is notoriously messy from a mathematical standpoint, with seemingly arbitrary parameters and asymmetric structures that offend physicists' aesthetic sensibilities. This raises a profound question. Is mathematical beauty a reliable guide to truth about the natural world, or is it simply a human preference that sometimes happens to align with reality? Some physicists argue that the universe is under no obligation to conform to our aesthetic preferences, that nature might be fundamentally messy and complicated, and that our search for elegant theories reflects our psychological needs rather than objective features of reality. Others maintain that mathematical beauty is indeed a reliable indicator of deep truth. They point to the historical success of theories that initially seemed beautiful but impractical, like Einstein's relativity or the mathematical frameworks of quantum mechanics. These theories were often developed based on aesthetic and mathematical considerations long before their practical implications were understood or their predictions were experimentally confirmed. The argument for beauty as a guide to truth often involves what physicists call the unreasonable effectiveness of mathematics. Mathematics is a human creation developed to solve practical problems and satisfy intellectual curiosity. Yet mathematical structures and relationships discovered in purely abstract contexts often turn out to describe physical phenomena with uncanny accuracy. It's as if the universe is written in a mathematical language that we're slowly learning to read. String theory represents perhaps the most extreme test of this principle. The theory is so mathematically complex and its connection to experiments so tenuous that it's primarily evaluated on aesthetic and mathematical grounds. If string theory is correct, it would represent a triumph of mathematical beauty as a guide to physical truth. If it's wrong, it might teach us that beauty alone is insufficient for understanding reality. There's also the question of whether mathematical beauty in physics reflects something objective about the structure of reality, or something subjective about how human minds work. Perhaps we find certain mathematical structures beautiful because our brains evolved to detect patterns and relationships that actually exist in nature. Or perhaps our aesthetic sense is simply a byproduct of how our minds process information, with no deeper significance for understanding the universe. The beauty of string theory has certainly influenced the direction of physics research over the past several decades. The theory's mathematical elegance has attracted some of the most talented minds in theoretical physics, leading to rapid development of sophisticated mathematical tools and techniques. But it has also led to criticism that the field has become too focused on mathematical aesthetics at the expense of empirical connection. As you settle into the gentle rhythms of approaching sleep, you might reflect on this deep mystery of mathematical beauty in the description of nature. Whether string theory ultimately proves correct or not, it has revealed mathematical structures of extraordinary richness and elegance. These structures exist in the realm of human thought and imagination, but they might also describe the fundamental architecture of reality itself. In the space between waking and sleeping, between the mathematical and the physical, between beauty and truth, lies one of the deepest questions about the nature of existence. Is the universe really made of music? And if so, are we learning to hear its song? If string theory is right, then reality is far stranger, more musical, and more interconnected than our ancestors ever dreamed. After wandering through dimensions both hidden and vast, after contemplating vibrating strings and holographic projections, supersymmetric shadows and infinite multiverses, we arrive at perhaps the most important question of all. What would it actually mean if string theory is correct? How would this change our understanding of who we are, where we come from, and what it means to exist in this universe? If string theory is right, then the most basic fact about reality is that it's made of music. Every particle, every force, every field, every bit of matter and energy in the universe would be nothing more than different vibrations of the same fundamental strings. The electron in every atom of your body, the photons carrying the light you see, the gravitational field that keeps your feet on the ground, would all be different notes in the same cosmic symphony. This musical nature of reality would mean that the apparent diversity of the physical world, all the different particles and forces that seem so distinct from each other, is actually a kind of illusion. At the deepest level, everything would be the same thing, just vibrating in different ways. It's as if the entire universe were a vast orchestra where every instrument, from the tiniest piccolo to the mightiest bass drum, is actually the same fundamental instrument played in different ways. The implications of this unity are profound. It would mean that you are literally connected to everything else in the universe at the most basic level possible. The strings that make up your thoughts would be the same kinds of strings that make up distant stars, black holes, and galaxies. When you look up at the night sky, you wouldn't be looking at something foreign and separate, but at different expressions of the same underlying musical reality that you yourself are made of. String theory also suggests that space and time, the arena in which all experience takes place, might not be fundamental features of reality, but emergent properties that arise from deeper structures. Just as the smooth surface of a lake emerges from the complex interactions of countless water molecules, the space-time you move through might emerge from the interactions of vibrating strings in higher dimensional space. This emergence of space-time has staggering implications for our understanding of existence itself. It suggests that the categories through which you organize your experience, past and future, here and there, cause and effect, might be approximate descriptions that work well in everyday life, but break down when you probe the deepest levels of reality. At the string scale, the familiar distinctions between space and time, matter and energy, self and other, might dissolve into something far more unified and interconnected. The holographic principle carries this interconnectedness even further. If reality is truly holographic, then every part of the universe would contain information about every other part, like a vast cosmic hologram where each fragment reflects the whole. This would mean that in some deep sense, you already contain information about everything that exists or could exist. The boundaries between inside and outside, between observer and observed, between the map and the territory, would be revealed as useful approximations rather than fundamental features of reality. String theory's prediction of multiple dimensions also radically expands our conception of what exists. If there are indeed 6 extra dimensions folded up at every point in space, then reality would be far richer and more complex than our 3-dimensional experience suggests. You would be moving through these extra dimensions all the time without knowing it, like an ant crawling on the surface of a vast sculpture, unaware of the intricate 3-dimensional structure that surrounds its 2-dimensional path. The possibility of a multiverse adds yet another layer of strangeness to this picture. If string theory is correct, then what you think of as the universe might be just one bubble in an infinite foam of realities, each with its own laws of physics, its own particles, its own story. Every possible universe that can exist mathematically might exist somewhere in this vast landscape of realities. This would mean that every choice not made, every possibility not realized in our universe is actually realized somewhere else. From this perspective, the question isn't whether other realities exist, but whether you can ever access them or communicate with them. You would be forever trapped in your own branch of the multiverse, able to contemplate the infinite garden of possibilities, but never able to visit the other flowers. String theory also suggests a deep relationship between information and reality that could transform our understanding of consciousness and experience. If the holographic principle is correct, then what you experience as physical reality might be better understood as information processing, a cosmic computation where the processing itself is the reality rather than something separate from it. This informational view of reality connects to some of the deepest questions about consciousness and subjective experience. If reality is fundamentally informational, then consciousness might not be something separate from physical reality, but a particular way that the universe processes and experiences information about itself. You might be, in the most literal sense, the universe becoming conscious of itself through the information processing that constitutes your thoughts and experiences. The mathematical beauty and consistency of string theory also suggests something profound about the relationship between human thought and the structure of reality. The fact that abstract mathematical structures invented by human minds seem to describe the deepest features of nature suggests either that our minds are extraordinarily well adapted to understanding reality, or that reality itself has a fundamentally mathematical character. If string theory is correct, then mathematics wouldn't be a human invention for describing nature, but a discovery of relationships that actually exist in the fabric of reality itself. The equations and symmetries and geometric structures that physicists study would be glimpses of the actual architecture of existence, the cosmic source code from which everything emerges. But perhaps the most profound implication of string theory is what it suggests about the nature of existence itself. If reality is made of vibrating strings in higher dimensional space, if spacetime emerges from more fundamental structures, if consciousness and information and mathematics are all aspects of the same underlying processes, then existence itself might be far more miraculous and mysterious than our everyday experience suggests. You wouldn't be a separate entity moving through an independent universe, but a temporary pattern in the cosmic music, a brief theme in the infinite symphony of existence. Your thoughts, your dreams, your sense of being a unique individual would be real and meaningful, but they would also be expressions of something far larger and more interconnected than you normally imagine. String theory doesn't answer the ultimate questions about why anything exists at all, why there is something rather than nothing, or why reality has the particular character it does. But it does suggest that reality is far stranger, far more unified, and far more beautiful than our ancestors could have imagined. If the theory is correct, then you are not just in the universe, you are the universe, experiencing itself from one particular perspective in the vast symphony of cosmic consciousness. And so, we find ourselves at the end of our gentle journey through the possibility that everything might be music. We've wandered through dimensions both hidden and vast, listened to the cosmic symphony that might be playing at the heart of every atom, and imagined realities far stranger than our everyday world suggests. Whether string theory is the final answer or simply humanity's most beautiful attempt to understand the cosmos, it reminds us that reality might be far more elegant and interconnected than we ever dared imagine. Every breath you take, every heartbeat, every thought drifting through your mind as you settle into sleep, if the strings are real, they're all part of the same magnificent song. We've seen how the smallest vibrations might create the largest structures, how hidden dimensions might be folded into every point of space, how the forces that govern stars and the particles that make up atoms might all dance to the same underlying rhythm. We've contemplated mirror worlds of supersymmetric partners, holographic projections that might contain all of reality, and infinite gardens of possible universes blooming in the mathematical landscape. Through it all, string theory offers us a vision of profound unity. The apparent diversity of the world, all the different particles and forces and phenomena that seem so distinct from each other, might be different expressions of the same fundamental music. If this is true, then you are literally connected to everything else in the universe at the deepest possible level, made of the same cosmic strings that vibrate in distant galaxies and black holes. Tonight, as your own vibrations slow and settle into the rhythm of rest, perhaps you'll carry with you a sense of wonder for the hidden music that might be playing all around us. The strings too small to see, the dimensions too folded to touch, the symphony too vast to hear, all of it weaving together the fabric of everything that is. Whether we live in a universe of vibrating strings or not, the search for understanding has led us to contemplate possibilities more beautiful and strange than our ancestors ever imagined. It's reminded us that reality might be fundamentally musical, fundamentally mathematical, fundamentally interconnected in ways that transcend our everyday experience. And if you found any peace in this quiet exploration, if the possibility of cosmic music helped you drift toward your dreams, we'd be honored if you follow us for more gentle journeys through the mysteries of science. Thanks for joining us here at Sleep Science. Sleep well, and may your dreams be filled with the music of the spheres.